Everybody. Accidentally started this recording. Started working on this problem without turning on my webcam, so I do apologize for that. Let me just select everything. We'll just get rid of it. And we'll start fresh. All right. Hope you're all having a wonderful time so far. Just getting all set up. So we want to talk about section 4.5, which has to do with optimization. Okay? Now, I'm willing to say, for the record, this is probably the most important lesson of calculus. And it all comes down to the idea that the optimal or best choice is almost always a critical point. Coming back from what we talked about last video, where we were finding these critical points. F prime of x sub p equals 0. And what we're going to find is anything that has to do with optimization, anything that has to do with choosing the best answer, or a lot of times you're going to get these as maximums or minimums, and we saw why there are maximums and minimums in the last video. But anything to do with these maximum and minimums usually has to do with some sort of critical point. Okay, so I actually want to do one of the first questions from your homework, just because I think it's useful and interesting. Let me just type it out just so we can be very clear by what we're trying to answer. That says find positive numbers x and y satisfying x times y equals 15 such that the sum 3x plus y is as small as possible. And this is going to be our first question. So we're going to break this down into its pieces, okay? And these are some common pieces that I'm going to suggest that you go looking for in each of these. So number one, you have a target or a goal to be minimized or maximized. Now, a couple things that I want to mention. Something that we almost always want to minimize in application. We like to minimize costs, right? We like to minimize harm. We like to minimize bad things. We also like to maximize profit, good things, expectations, right? So normally we're going to have a target. And so what is our target? Specifically, this 3x plus y small is going to be minimized. So what's our target? 3x plus y to be minimized. Okay. Now, with most of these, you want to minimize it? Just choose x and y both equal to the smallest positive number. We also are going to include some sort of relationship, or a better word is to talk about a constraint, a condition, something that's going to choose our values for us. Why can't we just choose x and y both equal to the smallest number? Well, because we have to choose, according to this condition, all our choices for x and y have to satisfy that x times y equals 15. That's our condition. So the goal is, what are all of the values coming from this that will minimize this? Okay? So that's just the setup. Pretty much all of these questions you're going to set up in this way. You're going to have a target, and you're also going to have a relationship. And you might have multiple relationships, but you usually only have one target. So how do we find the solution? Okay? Step one. Solve your constraint for a variable. Usually it doesn't matter which one you choose. So let's say we have x times y equals 15. Let's solve that somewhat arbitrarily. I'm just going to solve it for x. And I get x equals 15 over y. There's my step one. Okay. Step two, plug solution or solutions into your target. So 3x plus y is now going to be 3 times 15 over y plus y. And the hint is that you want to make a function of one variable. Now, we do want to sort of multiply this out. So I'm going to instead write our constraint as 45 over y plus y. So we found our solution from the constraint. We plugged it into the target. Now we're on to step 3. We're going to take a derivative, okay, of the target. So I'm just going to say take a derivative of the new target. So this is 45 over y plus y. And we're going to take a derivative in respect to y. Now, please note, when you get it a function of one variable, it should be very obvious which derivative you're going to take the derivative with respect to, which variable. In this case, I only have y, so I'll take a derivative with respect to y. Before we go any further, I'm actually going to rewrite this. I always like to rewrite this as the reciprocal, using the negative value, just because I think it makes it a little bit easier. So this is going to be 45 times, bring the power down and reduce it by 1, plus the derivative of y with respect to y is going to give me 1 times y to the 0. Simplifying that down, negative 1 times 45 is going to be negative 45 over y squared. I'm going to go back to the non-negative. Plus y to the 0 times 1 is just 1. So we take a derivative of the new target function and we get this, which is our new target function. And last but not least, step 4, we want to find critical points. AKA, you're going to set the derivative equal to 0. So I'm going to take negative 45 over y squared plus 1. I'm going to set that equal to 0. How do we solve this? Well, one of the easiest ways that you can solve this is you multiply both sides by y squared. You're going to get negative 45 plus y squared equals 0. And we can move that over by adding 45. Y squared equals 45. Or by doing a square root. Now, keep in mind, we're only going to take a look at the positive square root. Why? Don't get motion sickness. Taking you back over here. Remember, at the very beginning, it says find positive numbers. So we know x and y are both going to be positive. We can, in this specific circumstance, we can ignore the negative. That's not always true, but in this circumstance we can. And look at that. You get y equals 45. Okay? Now, this is half the story. Oh, I'm sorry. Apologize. Y is not 45. Y is the square root of 45, which we also want to separate. Keep in mind, 45 is 5 times 9. I don't know the square root of 5, but I do know the square root of 9 is 3. So I'm actually going to write that y is 3 times the square root of 5. Now, that's only half the story. Step 4 was to find the critical points. There's usually a 5th step. Plug the critical point into the constraint. Now, some questions ask for this, some don't. Some want the target, for example. We'll talk about all the different things you can ask for. But we are going to plug this critical point back into the constraint. So just reminding ourselves, what was the constraint? The constraint was x equals 15 over y. X equals 15 over y. But, going back to problem number 4, we actually know y is 3 times the square root of 5. Now, how do we solve this? First things first, I'm going to multiply both sides by the square root of 5. And that's just to try and simplify this denominator. This is going to be 15 times the square root of 5 over 3 times 5. Because remember, square root of 5 times square root of 5 is 5. Now, 3 times 5 is 15. This is going to be 15 times the square root of 5 over 15. Or x is the square root of 5. So putting these two things together, my solution is x is the square root of 5, and y is 3 times the square root of 5. That is the solution to what is the smallest pair of numbers that multiply to equal 15, that 3x plus y is as small as possible. And in fact, it turns out to be 6 times the square root of 5. Any other pair of numbers is going to be worse. Now, let's go back over those steps one more time, just to make sure. So, before you do anything, you always want to make sure you know these two pieces. Do you know the constraint and the target? Make sure you have those written down. Then, what are we going to do? We're going to solve the constraint, plug it into the target, take a derivative, find the critical points, and plug that critical point back into the constraint. Now, there might be multiples. What if there are more than one? Answer: check them all in the target. One of them is going to work, right? Sometimes you might get multiple answers. Like, for example, if this was not specifying positive numbers, theoretically, we would have gotten two answers here, a square and a negative. But again, one of those is going to work. It has to, right? And so that's something that you can use to kind of make it a little bit easier. You know it's going to work, and you know one of them is going to work. The critical points are all of the possibilities that are going to work, okay? So always, always, always try to make sure. Now, a lot of these ones that we're going to take a look at, and I'd be happy to do as many of them as you would like, but a lot of these require some good pictures. So let's go over. Let's do another one. And I'm just looking at your homework. So if you guys have some questions, please, 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 please send me some, and I'd be more than happy to do a video on them. One of the more famous ones is sometimes called the area problem. In fact, I'm going to grab this out from your homework real quick, and just bring it on screen. A rectangular pin is built with one side against a barn. If 500 meters of fencing are used for the 3 other sides, what dimension to maximize the area? Please ignore this picture. We're going to just do the first one. So again, we need a target and a constraint. So in part A, we want to maximize area. So let's get our picture going. So here's our barn. And our barn continues on. And we want to build a rectangular pen with what I will call a length L and a width W. And we want to maximize the area, which is length times width. Or, in other words, area equals length times width. Now, what is our constraint? We only have 500 meters of fencing. If you want the largest fence possible, just use up a bunch of fencing. But that's not realistic. We have some maximum amount of fencing that we've purchased. So the question is, what should we make? What should we choose for L and W such that our choice will maximize this area? Well, we need this constraint in an equation. Something equals 500. And it's going to be what we construct. And notice we construct L plus 2W. Now, please note, if you label these differently, if you decided to call this X or this Y, you would get a different set, right? Your answer would look different, but we're still talking about the same construction. So you don't have to worry as much about what you choose. I like to choose things that make sense to me. I think of this as a length. I think of this as a width. So we can do this. So just to remind ourselves, we have our target. Let me use a different color. A equals L times W. And we have our constraint. 500 equals L plus 2W. So, do you remember the rules? We're going to solve the constraint, plug it into the target, take a derivative, find the critical points, and then we'll go back into the constraint. What does that look like? Apologies, another phone call. I should really figure out what time I'm recording these and tell people to stop calling me. So, step 1, we're going to solve the constraint. And I'm going to choose very arbitrarily. I'm going to solve for L. So we have 500 equals L plus 2W. Solve that for L. I'll subtract 2W. I'll get L equals 500 minus 2W. Step 1, done. Step 2, plug that into my constraint. Into my target. L times W. We're going to take this L. We're going to plug it in right there. And we're going to get A equals 500 minus 2W times W. Now, it's a good idea to multiply these out only because you're going to find that you're going to take some derivatives. And usually, if you multiply them out, it's a little bit easier to find the derivative. But there is our new target to be maximized. Step 3, what are we going to do? We're going to take a derivative. And we're going to take a derivative with respect to the only variable that appears, W, of 500 W minus 2W squared. Polynomial, 500 minus 4W. There's our derivative. Step 4, we're going to plug this and find the critical points. We want to solve 500 minus 4W equals 0. So how can we solve that? Just a linear equation. We'll add 4W to both sides. 500 equals 4W. Kind of anticlimactic. We're going to divide by 4, and writing it left to right, I think we get W equals 125. I should check that on a calculator. I've made too many mistakes making these videos. Yeah, we get 125. Now remember, this is not the end of the story, because also we want to go back to our constraint, 500 minus 4w, and we want to plug that value back in. And that's going to look like 500 minus 4w, and by the way, this is L, but instead of w, I'm going to write what I know w to be, which is 125. This is 500 minus 4 times 125, 500. What's that? We get 0. 0. Now, what does that tell us? Well, theoretically, we're going to maximize or minimize the amount of area according to our constructing this. We just need to choose L to be 0. And if you think about it, if you choose L to be 0, in a way, you have minimized the function, right? You've created a barn that doesn't have any any area to have. But remember, we wanted to maximize this function. So why did we get a minimize instead of a maximize? Oh, hang on, I'm getting another call. Apologies for that interruption, but I want to point out we were looking for the maximum. So we know that an area of 0 is going to minimize. And that's always a good thing, conceptually, to understand the boundaries. But let's plug that back into the constraint. Let's plug our solution back into the constraint, which, reminder, our constraint was 500 equals L plus 2W. And if W is 125, this is 500 equals L plus 2 times 125, or 500 equals L plus 250. That one I'm confident to do in my head. And just like that, we get that L equals 250. Now please note, this represents the maximum, whereas the 0 represents the minimum. Okay. Now theoretically, there's another one, which is 500, if you think about letting W be 0. But most of the time, these questions are set up in such a way that we want to solve for an obvious maximum or minimum. There's not usually any of these where it's like, wait, are we trying to minimize something or maximize something? Usually they're pretty straightforward. So what is our answer? Well, we got L is 250, and W is 125. Now, that is the dimensions. But what is A? Well, A is L times W, which is 250 times 125. Now, I must confess, this one I'm not so confident to do in my head. But my calculator told me 31,250 square meters, which sounds like quite a few meters. So I'm willing to believe it. Now, again, the important thing here is to recognize that the process is identical. Once we have a target and a constraint, we solve the constraint, plug it into the target, take a derivative, set equal to 0, and we plug that critical point back into the constraint. So let's do one more directly. In fact, I don't want to do this next problem, but I do want to give you a hint on part B. Hint. Part B, by the way, this is question number 6. Same thing, but we have our barn. Then you want to make fences, or should I say sub-fences, that each have 100 square meters. So the question is, again, what are the choices for L and W that will minimize the amount of fence that is used? Oh, I'm sorry. So now we're sort of flipping on our head. We know what the areas are going to be, but we don't know how much we have. So what is our target? What do we want to minimize? We want to minimize our perimeter, our fence size. And so what is our fence size? Well, we have 1, 2, 3, 4, 5. Oh, I also want to keep this consistent. So I like to call the long side the width and the short side the short side the width and the long side the length. So we want to target 1, 2, 3, 4, 5W plus L is minimized. And what is our constraint? Well, it must be true that each of these represents 100 square meters, and the area is going to be L over 4. So the constraint is 100 equals W times L over 4. So we're switching up where the equations went in terms of target and constraint. However, the same process totally works. Solve the constraint for one of your values. I suggest W. Plug it into the target, take a derivative, find the critical point, and then plug it back into the constraint. So hopefully this helps you. Again, if you have any other questions from this section that you want to take a look at, I'd be willing to do all of them. All you have to do is send me an email. I'll do any of them that you would like at any time. Please avail yourself of this, because I'd be more than happy. I want to know which ones you guys are struggling on so that I know you can give you your help, because there will be optimization problems on the exam. But other than that, I wish you a wonderful rest of your days, and I'll see you all in the next